This is Chapter 11, Torque and Rotational Dynamics. We're going to learn about torque in static equilibrium, and we'll also learn about its role in things that rotate. Another thing we'll learn is the effect that the shape of a spinning object has on spin rate.
All right, now let's talk about torque. All right, so everything about balance and center of mass was really just leading up to torque. From experience, we know that the same force will be much more effective at rotating an object, such as a nut, if our hand is not too close to the axis. So I don't know how many of you ever tried this, but if you try to unscrew something, let's suppose you want to take something apart or repair something, you don't have a wrench with you, and you try to just put your finger right on the nut. It's really hard. Sometimes we like to say in common language, you can't get leverage. Well, that idea of leverage comes from this concept of torque, because just as a lever is force at a distance, that's really how wrenches work. Wrenches work with torque. Force at a distance multiplies the force, and that distance r becomes a multiplier for the force. Now, if we look at this particular wrench here, we can see that if I grabbed the wrench here where the mouse arrow is tracing, I would need a much bigger force, F2. But if I grab it out here, right, at distance R1, the force required is much less. So we define a quantity called torque. Definition of torque, or tau, for a tangential force Ft, tau equals r Ft. It's simply the distance times the force, okay, or force times distance. The order doesn't matter. And the SI unit is Newton meter. Now, you may recognize this unit from the chapter on work and energy. And Newton meter is actually the unit for work and energy, but there's an important difference. All right, when we're talking about Newton meters with energy, those Newton meters are equivalent to joules, and it's a scalar quantity. In other words, energy and work are always scalars. They're not vectors. They don't have direction. They're just amounts. Torque, on the other hand, is a vector. It has a magnitude and a direction. And so even though it uses the units of Newton meters, just as work and energy does, it's not equivalent. All right, because one is a scalar, work and energy, and the other, torque, is a vector. So the torque increases as the force increases, and also as the distance increases. Only the tangential component Ft causes torque. So let's suppose we look at this image here on the left, and we have a boy swinging people around on a merry-go-round. Well, if he just pulls straight up, there's zero torque, right? There's going to be no component that's tangential to the circle. Now, if we look on the right-hand side, we can see that he's not pulling straight up anymore. He is at least pulling at an angle. And because he's pulling at an angle, there will be a tangential component to his force. And that tangential component, Ft, is what results in torque. Let's look at this problem. What is the torque on a bolt produced by a 15 Newton force exerted perpendicular to a wrench that is 25 centimeters long? All right, you should be able to figure this one out on your own. Pause the video, get your answer, and then resume when you have it. All right, so going through the solution, write our givens down, and notice that I can just write the formula tau equals Fr, or force times radius. You can also write it as force times distance, whatever variable you happen to be using. And so then just doing our plugging and chugging, I have 15 newtons times 0.25 meters. Notice that we convert the 25 centimeters to meters, and we have 3.8 Newton meters. A counterclockwise torque is positive. A clockwise torque is negative. All right, this is important to remember, and we'll see examples of it later in this video. But a positive torque is defined as a torque that is rotating or trying to rotate in the counterclockwise direction, And a negative torque is a torque that is rotating or trying to rotate in a clockwise direction. All right, and if you look at what would happen to these diagrams if you push down where the force vector is touching at that distance, well, sure enough, you would cause the resulting torque that the animations are showing. The vector nature of rotational motion, just as we saw in the last video of how the angular velocity omega and the angular acceleration alpha have direction, and the direction is provided by the right-hand rule. Well, torque operates exactly the same way. All right, the direction of torque is actually along the axis of rotation, and so we use our right-hand rule. The direction that your fingers would wrap around the rotating object, your thumb on your right hand would be pointing in the direction of the torque. All right, so the direction of the torque vector works just like the omega and alpha vectors. Conditions for static equilibrium. All right, before I talk about what's on this screen, let's just clarify what we mean by static equilibrium. We have seen it a few times this year, but as you can imagine, static just refers to something standing still. And so, like if you are standing on the ground, well, your force of weight is opposed by the normal force of the ground on you, and so you stay still because those two forces are equal and opposite. All right, so static equilibrium is just when things stand still. When things stand still. All right, so the conditions for static equilibrium. This happens when the net force acting on the object is zero, that is, the net horizontal force is zero and the net vertical force is zero, and two, the net torque acting on the object is zero, and that is the net tau, or the summation of all the different taus that there may be, torques, equals zero. Okay, so when you have an object or a system of objects in which there is no net force, that is, the forces cancel each other out, and no net torque because the torques cancel each other out, then you have static equilibrium. Now, as always, the best way to clarify concepts is by example, and so we're going to look at two examples of static equilibrium. All right, let's look at this example. We have a mother and father holding their toddler on a 1 meter plank, and the toddler weighs 200 newtons, and we can see that the little boy is closer to daddy and a little bit farther away from mommy. Okay, but this whole system is in static equilibrium. Everyone's just standing still. There's no motion going on. So we're asked to calculate F1 and F2. All right, now a very important thing when you're doing static equilibrium problems, and it's something that isn't quite intuitive at first. It's simply to pick an axis of rotation. Now you could just as easily pick the dad's hands as your axis of rotation. That's up to you. You pick the axis of rotation that you want. Personally, I find it's usually easier just to pick the axis of rotation that's farthest to the left, but that'll be up to you. The main thing is you need to pick an axis of rotation. All right, now how are we going to set this problem up? Well, we're going to set it up using the two conditions of static equilibrium that we just learned. First, the force condition. The net vertical force, because here we're only talking about vertical forces, would be F1 plus F2 minus 200N equals 0. And that makes sense, right? We know that if the weight vector of this toddler is going down, well, there must be an equal and opposite force pulling him up, keeping him from falling, and so that must be 200 as well. So we know that F1 plus F2 minus 200, they all cancel each other out, and we have 0, so net vertical force of 0. And now let's look at the torques. This might seem a little tricky at first, but just be patient and wait for the explanation. So the net torque equals 100 F2 minus 75 times 200 newtons, and that equals 0. So 0 net torque. Now let's see where these numbers came from. Alright, whenever you're doing these problems, as I said before, first you find your axis of rotation, and then what you do is you calculate one torque at a time, pretending that there's nothing else rotating about the axis but the torque that you're focusing on. Alright, so let's look first at Daddy's torque. Alright, well, if we look at Daddy's torque, and while you're doing that, you can pretend the little boy isn't even there. Alright, and if that's the case, then we have a force, F2, and that's going up, and it's at a distance of 100 centimeters. That's why I have 100 F2. 75 plus 25 is 100. A distance of 100 centimeters away from the axis of rotation. And also notice that 100 F2 is positive. It's positive because since F2 is going up, it would tend to create, or it's trying to create, a counterclockwise rotation. And remember that counterclockwise is always positive. Okay, now let's forget about Daddy for a second and let's look only at Junior. Alright, if we look only at Junior and forget about Daddy, let's calculate Junior's torque. Well, the distance of our little friend here from the axis of rotation is 75 centimeters. Now, because we're really only looking for forces here, and distances are always proportional, you don't have to convert to meters. You can if you want, and it'll come out exactly the same, but just for the sake of convenience, we're leaving it in centimeters. Alright, so I have 75, which is the distance from the axis of rotation to the toddler, times 200 newtons, which is the force. And notice since that force is going down, it would tend to create a clockwise rotation, and that's negative, and that's why I have minus 75 times 200n. Let's see. So all this is saying here, this net tau equals 100 F2 minus 75 times 200n equals 0. This is just saying that torque 1 minus torque 2 equals 0. The net torque is 0. Alright, so again, the first time you do these problems is kind of weird because we're not used to picking an axis of rotation. And also, since this system's at rest, we kind of have to think about how objects would rotate if they could. And we also need to kind of blank out objects when we're calculating individual torques because we only want to do one torque at a time. Alright, let's continue the solution then to this problem. Carrying forward the system, we have F1 plus F2 minus 200n equals 0, and 100 F2 minus 75 times 200n equals 0. F1 plus F2 equals 200, 100 F2 equals 75 times 200, and then solving for F2, I get F2 equals 150, and F1 equals 50. So F1 equals 50 newtons, and F2 equals 150 newtons. Okay, now this is a slightly harder example. It's good practice for torques. A school bus has an unloaded weight of 20,000 newtons. All right, all that means is when there are no people on the bus and no cargo and no weapons and all that stuff, the unloaded weight is 20,000 newtons. If I attach a 2,000 newton cow catcher to the front and a 5,000 newton torpedo to the back, what will be the normal force of the ground on each tire? Alright, well, let's go through this problem. Alright, if we look at our vectors, and remember it's always important to make sure the vectors are labeled correctly. Here I just gave you the drawing, but when the problem doesn't give you the drawing, you need to make sure that you take the time to sketch. Alright, so let's first of all look at our 20,000 newtons because that vector is always there when it's unloaded. And so that 20,000 newtons is going down straight into the ground from the center of mass of the bus. Alright, the center of mass of the bus. Now, of course, the center of mass of the bus would be a little bit higher up, like here, kind of this area where I'm tracing with the mouse arrow right now, it'd be higher up. But for the sake of clarity, we're just drawing it a little bit lower. Okay, so we have the 20,000 newtons there. We have the 2,000 newtons coming straight down from the center of gravity of the cowcatcher. And then we also have the 5,000 newtons coming straight down from the torpedo. Okay, now F1 and F2 would be normal forces, forces that go straight up. And obviously we know that the total amount of normal force has to cancel the total amount of downward force. Now let's look at these distances. We have a distance of 1.20 meters from the center of mass of the cowcatcher to the center of the first tire. Then we have 2.40 meters from the center of that first tire to the center of mass of the bus, 4.8 from the center of mass of the bus to the center of the back tire, and 3.6 from the center of the back tire to the center of mass of the torpedo. Now, those distances are just given to you, all right? So they're going to be part of how we solve the problem. So the important thing for this problem is similar to the last example. It's more complicated, but it's still the same type of process. You have to set it up according to the two conditions of static equilibrium. So let's look at the force condition. The net vertical force equals F1 plus F2 minus 27,000. 27,000 is just 20,000 plus 5,000 plus 2,000. So we have F1 plus F2 minus 27,000 equals 0. Okay, now the torque part, the torque part of this problem is a little bit more complicated. So I'm going to put the torque equation here for you, and then I'll go through it step by step. Okay, so now for the torque equation. First, we're going to mark our axis of rotation. And notice that on the front tire of the bus, I'm now placing a green dot. And that green dot will be our chosen axis of rotation. All right, now the torque equation will look like this. The net tau equals 2,000 times 1.20 minus 20,000 times 2.40 plus F2 times 7.20 minus 5,000 times 10.80 equals 0. Alright, so as I did in the last example, I'm going to go through each of these elements step by step. Alright, let's look first at the 2,000 times 1.2. Remember that with the torques, we want to look at one torque at a time, pretending the others don't exist. Alright, so just kind of ignoring the rest of the bus. All we're doing is we're looking at our axis of rotation, and we're looking at this one torque, the cowcatcher torque. We have a downward force, and we have a distance of 1.20. And the reason why it's positive 2,000 times 1.20 is because that downward force with this distance of 1.20 would tend to cause, if it could, a counterclockwise rotation, and that's positive. Alright, moving on to the next torque. Now we are looking at the torque of the bus's unloaded weight. And so that is a downward vector of 20,000 newtons. Its distance from the axis of rotation is 2.40 meters. And it's negative because that downward force at this distance from the axis of rotation is trying to create, as you can see, kind of this portion that I'm circling now with the mouse arrow. That downward force of 20,000 at a distance of 2.40 from the axis is trying to create, as if it could, a clockwise rotation. And therefore I use negative 20,000 times 2.40. Alright, moving on now to the next torque. Well, we have this upward force of F2. And this upward force of F2, which is the normal force on the back tire, is a distance of 2.4 plus 4.8, which is 7.20 meters from the axis of rotation. And so right now, pretending all the other torques don't exist, and just concentrating on this F2 force and this 7.20 distance that I'm kind of circling now with the mouse arrow. If I just look at that one big torque, I can see that the upward force at that distance from the axis is trying to create a counterclockwise rotation, hence the positive sign. All right, only one more torque to account for, and that would be the torpedo torque. And so if I look at this torpedo, I've got the 5,000 Newton force going straight down, and it's at a distance from the green dot, the axis of rotation, a distance of 10.80 meters. And you can count these up and verify. 2.4 plus 4.8 plus 3.6 is 10.8. All right, and so if you look at this, pretending the other torques don't exist, this torpedo with a downward vector at a distance of 10.8 from the axis is trying to create a clockwise rotation, and that's why I have negative 5,000. All right, so this is the torque equation and where it comes from. Now, for practice, I'd like you to do what's on the next screen on your own first, which is the solution of this system, and then resume the video when you have some answers for that. All right, so we carry our system forward. The force equation, F1 plus F2 minus 27,000 equals 0, and the torque equation, 2,000 times 1.20, etc., equals 0. Now I have F1 plus F2 equals 27,000. Just rearrange the first equation a bit. And I can evaluate what I can of the second equation. So I have 2,400 minus 48,000 plus 7.20 F2 minus 54,000 equals 0. Then I simply get F2 by itself on the left and constants by themselves, a constant by itself on the right. And now I solve for F2 and I get 13,833.33. Plug that back into the first equation, F1 plus 13,833.33 equals 27,000, and therefore F1 equals 13,166.67. So F1 equals 13.2 kilonewtons, which is of course the same as 1.32 times 10 to the fourth newtons, 13.2 kilonewtons, and F2 equals 13.8 kilonewtons. Let's look at this problem. On the beam below, calculate the normal forces Fp and Fs. Disregard the mass of the beam. All right, to explain this problem a little bit, so we just have two pillars here supporting the beam, pillar P and pillar S, and the beam it's got weights hanging on it. One weight is 40 newtons and the other weight is 20 newtons. Okay, and so we can see that there's a downward force of 40 newtons on one side, a downward force of 20 newtons on the other side, and in the middle we have two upward forces. Those are going to be Fp and Fs, two upward or normal forces. Alright, so using the techniques you've learned with the bus example, you're going to try to do this problem on your own. Now, you may have to do it in a couple of parts. What I mean by that is you might want to pause now and then try to figure out your equations, and then resume just to make sure you have the right equations, and then pause again to do some more calculation, and then resume to make sure that your steps are right. Torque problems are hard, and so don't be surprised if you have to resume periodically just to make sure you're doing things right. Alright, but do pause now and try to come up with the equations of static equilibrium. Remember that one equation is going to be a force equation and the other equation will be a torque equation. And when you get those two, you can solve the system. Alright, let's go now through the solution. The first thing is to come up with your equations. And so we have our force equation and our torque equation. Alright, looking at the force equation, we have two upward forces, Fp and Fs, and we have two downward forces of 40 newtons and 20 newtons. Well, if you add 40 and 20, you get 60, and that's why I have minus 60, because that's 60 newtons going down. That must equal 0. Now we have our torque equation. Let's look at these torques here. Well, if we pick pillar P as our axis of rotation, well, then we do one torque at a time in reference to that pillar P. So we look at 40 newtons times 10 centimeters, or 0.10 meters. And 40 times 0.10 would be a torque. If this could move, right, it would move in a circle that I'm tracing now with the mouse arrow. If it could move, all right, this 40 newtons would be tending to cause a counterclockwise rotation. And since that rotation is counterclockwise, we have a positive torque. Now moving on to the next torque, remember that P is our pivot point, or our axis of rotation. So since everything revolves around that, that wouldn't be included in the torques. And so our next torque then is moving over to Fs. Fs is an upward force. We have an upward force, and Fs is a certain distance, 20 centimeters away from the axis of rotation. And that's why I have written here Fs times 0.20. Now, why is it positive? Because if you look at this force, which is going up, and if you pretend that the whole thing could move, well, this upward force would cause the whole beam to move in a counterclockwise direction. And counterclockwise is positive. And finally, our last torque on the right here would be the 20 newtons going down. That 20 newtons is a distance of 40 centimeters from the axis of rotation, and that's 0.40 meters. So we have 20 times 0.40 meters. Now notice the negative sign. That's because if this beam could rotate, 20 newtons pulling down would cause a clockwise rotation of the beam, and clockwise is negative when you're dealing with torques. Okay, so continuing with the solution, we just carry our equations forward, and then we can work with the torque equation. So just doing the calculation there, we end up with 4.0 plus 0.20 Fs minus 8.0 equals 0. And then doing some algebra on that, we end up with Fs equals 20 newtons. And then putting that 20 newtons, that Fs, back into the force equation, we can solve for Fp and find that Fp is 40 newtons. And so the upward force Fs is 20 newtons, and the upward force Fp is 40 newtons. Moment of inertia. And this is a little hard to understand at first, so I'm going to spend a little time just, explaining the concept. Just as mass inherently resists a change in motion, which Newton's first law tells us, mass also resists a change in rotation. All right, so we know that Newton's first law says that objects at rest tend to stay at rest, objects in motion tend to stay in motion. All right, so that's nothing new. The law of inertia. All right, now this law also applies to rotation. So, an object that can rotate resists rotation, or if it's already rotating at constant velocity, it resists stopping. So it's just the rotational equivalent of Newton's first law. So imagine a massive stone revolving door. All right, pretend that there's no friction on the pivot. It's freely revolving. It's massive, weighs several tons. Now, a door like that, you can kind of just picture it. It's not going to be easy to open. All right, you have to push hard because it's a large mass, and to get that mass to accelerate from rest to any velocity requires force. Okay, so you can this is kind of intuitive, the fact that an object resists rotation, just as an object resists being pushed in a straight line. Consider this windmill. Will it turn if 10 people blow on it? Of course not. That's ludicrous. You need a decent sized wind to get something like this going. The rotating mass is too large and much of the mass is far from the axis. All right, there are two things going on here. First of all, let's go back to linear motion. With linear motion, just pushing something in a straight line, it really just depends on the mass. But when you're rotating something, it doesn't just depend on the size or the magnitude of the mass. It also depends on how much of that mass is far from the axis of rotation. All right, if a lot of it is far, it's going to be harder to rotate than if not much of it is far. All right, now we'll talk a little bit more about this on the next few slides, but that's the main thing to start to understand, is that rotational inertia basically depends on two factors, the mass and the radius. All right, to clarify that last point, let's look at this example. I've got two propellers here. They are different shapes and different sizes, but they have the same mass. If you like, you can think of the one on the left made of some kind of plastic and the one on the right made of some kind of really dense metal. In any case, they have the same mass, 75 kilograms. They have different radii. The one on the left has a radius of 36 centimeters. The one on the right, a radius of 60 centimeters. Okay, just checking your common sense. All right, this is not calculating, it's just conceptual still. I want you to think about which of these two, keeping in mind that they have the same mass, which of these two is going to be harder to rotate. Pause the video, think about that, and when you have a mental answer, resume. Is this what you came up with? A motor has to work harder to accelerate the propeller on the right, because most of the right-hand propeller's mass is distributed away from the axis of rotation. Most of the left-hand propeller's mass is close to the axis of rotation. All right, so what you have to keep in mind when we're talking about the moment of inertia, and we are going to define this concept. Right now, I just want to set the kind of conceptual foundation, is that the moment of inertia, or rotational inertia, how much an object resists rotation, depends on its mass, and also how much of that mass is far away from the axis. So it depends on mass, depends on radius, depends on the distribution of mass away from the axis of rotation. Continuing our discussion of the moment of inertia. An object's resistance to change in rotational motion is called its moment of inertia. All right, that's all we mean by moment of inertia, is that. Okay, so it depends on both the object's total mass and the distribution of its mass in relation to its axis of rotation. That's kind of what I was referring to in the previous slides. Okay, so what we have to think about here is that moment of inertia is probably not the best term, and I'm just saying this, I guess, from personal experience too. When you first hear the word moment of inertia, you don't think of mass. You think of, I don't know, time, moment, moments to remember, the moment of truth. We tend to think of moment as time, but it's not. This is just a term, okay? So moment of inertia really refers to mass above all else, and it refers to mass in relation to its radius. All right, so just think of moment of inertia as rotational mass or rotationally affected mass. For example, if the solid wheel and the spoked wheel below have the same mass of 10 kilograms, it will require more torque to accelerate the spoked wheel. So here we have two objects with the same mass and the same radius. And yet, if we look closely, we can see that the spoked wheel has a lot more of its mass far away from the axis of rotation. And that's why it's going to be harder to rotate. Okay, so if we're looking at these two identical objects except for the fact that one is spoked and the other is solid, we can tell that moment of inertia or the resistance to change in rotational motion, depends on both mass and the distribution of that mass about the axis of rotation. Therefore, the spoked wheel has a bigger moment of inertia than the solid wheel, even though each has the same mass. If it helps you, think of an object's moment of inertia as its rotationally affected mass. Okay, so if we're thinking of a mass that we're going to push just in a straight line, going back to that familiar example, you're going to push something in a straight line along a frictionless surface. Well, it's just, going to take a certain amount of force to accelerate it. And all that depends on is the magnitude of the mass. But when things are rotating, the moment of inertia depends not only on the mass, as I've already said, but also on the radius and how the mass is distributed according to that radius. Is most of the mass far from the axis of rotation, or is most of it close? That's what determines moment of inertia. All right, so moving on with this discussion. Any solid object can be thought of as a whole bunch of point masses stuck together. So let's look at this. Let's look at this cylinder, and let's think of it it's a solid cylinder. You can think of it as a solid lead cylinder if you like. And what all these little dots represent, they represent tiny little points of mass. If you want to, you can think of them as atoms. And each one is a tiny little particle of mass. And so obviously this large solid object is made up of many, many, many tiny particles of mass. Okay, that's not a new concept. You already are familiar with atoms, you took chemistry, you know that bodies have cells, etc. So big things are made up of small things, nothing new there. The sum of the masses and energies of the point masses equals the total mass and energy of the object. Okay, so like let's say that you are speeding down the highway at 85 miles per hour, and please don't do that, very unsafe. But let's say that you are speeding down the highway at 85 miles per hour. Well, obviously your body has a speed of 85 miles per hour, and every cell in your body has a speed of 85 miles per hour. All right, let's say that you have a certain momentum as you're traveling in your car. Well, your total mass times your velocity equals the mass times the velocity of every little cell in your body. All right, so it's really just the whole is the sum of its parts. There's nothing new here, right? The whole is the sum of its parts. So the masses and energies of all the point masses equals the total mass and energy of the object. All right, so now we're going to derive the definition of moment of inertia. So the ladybug represents a rotating point mass m. Now, obviously, the ladybug is big enough to see because we're trying to learn here, but a point mass is just that. It's a point, something that you would not even be able to see. It's so small. But for the sake of clarity, let's just imagine that the ladybug is a point mass, right? Tiny little particle that's been magnified. And it's rotating. It's rotating with a radius r. And it's also accelerating. It has a tangential force Ft, so that force which is tangent to the circular motion. And that force is causing a tangential acceleration At. All right, so let's lay this out. We know that Ft equals mat because it's just Newton's second law, F equals ma. And now from the last section we learned that At equals r alpha. And you may want to refer to previous notes. It's always a good idea since everything in math and science depends on earlier stuff. All right, so we have Ft equals mr alpha. And we also know from the last section that torque equals rft, r the distance, right, from the center to the outside. That's torque by definition. So torque equals rft. And that simply equals mr squared alpha. Okay, all we did there is we replaced the ft with mr alpha, and so r times mr alpha is just mr squared alpha. Okay, so these three steps add up logically. We have torque equals mr squared alpha. And now we come to the definition of the moment of inertia. The moment of inertia of a point mass is defined as I equals mr squared. Now I know that we used I as the abbreviation for impulse earlier. And this is one of those cases where we actually have two realities represented by the same symbol. But of course you just tell by context which one is meant. So the moment of inertia of a point mass is defined as I equals mr squared. The SI unit is kilograms meters squared. And that makes sense because it's just mass, which is kilograms, times r squared, and r is a distance, so it's m squared, meters squared. So the SI unit of moment of inertia is kilograms meters squared. So here's the key to understanding moment of inertia, and it's based on the last slide. The sum of the moments of inertia of the point masses in any solid object equals the total moment of inertia of the object. All right, so if you go back to that cylinder filled with dots, you can picture it, right? The moment of inertia of all those dots, adding that all together, is going to equal the total moment of inertia of that solid cylinder. Okay, so it's still based on that simple concept of the whole is the sum of its parts. So the sum of the moments of inertia of the point masses in any solid object equals the total moment of inertia of the object. And this brings us to torque equals I alpha. All right, torque equals I alpha. Now, where do we get this? Okay, so you can, if you just kind of look up here, see where it comes from. See, I already was able to define torque as mr squared alpha. And so if I just look at this mr squared here, which is part of that equation, well, I can replace it now that I've defined moment of inertia. I can just replace it with the symbol I. And that's what I've done down here. So I have that mr squared being replaced by I by definition, and therefore torque equals I alpha. Torque equals I alpha is the rotational equivalent of F equals ma. All right, and that makes sense. In fact, if you think about all this rotational stuff, it's all analogous to the linear stuff. All right, the angular displacement theta was analogous to the linear displacement s. We saw that in the last section. Or the angular velocity omega is analogous to the linear velocity or the tangential velocity. All right. Same is true of the angular acceleration. They all of these rotational concepts have equivalents, linear equivalents, right? And all the linear concepts have rotational equivalents. And because of those similarities, it becomes a little bit easier to calculate this stuff and to conceptualize it. All right, so you can see the similarity here. You know that alpha is analogous to A, and I is analogous to little m, and tau is analogous to F, and so T equals IA, or rather, better said, torque equals I alpha, is the rotational equivalent of F equals ma. All right, these are moments of inertia of various regular objects. Okay, so what we have here is we have some solids. We have some solids of different shapes and mass distributions. And you can see that they all have something in common, mr squared. All right, they all have mr squared, but multiplied by different fractions. Now, those fractions are figured out from calculus. And this is one of those cases where really doing the proof of each of these does require you to understand integrals, which is something you'll learn in calculus. But the moments of inertia can be calculated just by doing the appropriate integration. And those of you who are in calculus now will kind of know what I mean, although I'm not sure if you're on integration yet. You might still be on um, derivatives. But in any case, whether you're in calculus or not, it's really not too hard to just write these formulas down, because they're true of any shape like this. And there are, of course, lists of other moments of inertia for other kinds of shapes, but these are really the only four that we're going to deal with for now. So you definitely want to write these down because you'll need to refer to them. And you don't have to worry about memorizing them, because although I do require you to remember formulas, I consider these just table information stuff. And so like on a test, I would definitely give you this information. Okay, these aren't formulas to memorize. But the neat thing to point out here in this slide is that any regular shape, um, for any regular shape, you can calculate using calculus integration the moment of inertia. Okay, and you can see, let's just look at these two at the top. Well, the hoop, or cylindrical shell, has a moment of inertia of mr squared, which, as you'll see, is identical to that of a point mass, because if you look at it, this is really equivalent to a bunch of point masses just going around with hollow space in the middle. Now, if you look at the disk over here on the right, 1/2 mr squared, okay, it has a smaller moment of inertia because more of the mass is closer to the axis of rotation. Looking down here at the hollow sphere has a moment of inertia of 2/3 mr squared, whereas the solid sphere has a moment of inertia of 2/5 mr squared. All right, and so again, we can see that the hollow shape has a larger moment of inertia because more of the mass is concentrated far away from the axis of rotation, whereas with the solid sphere, a lot of that mass is close to the axis of rotation, therefore that makes it easier to rotate. And so it would be considered to have a smaller moment of inertia. All right, so make sure you have these formulas written down. Remember that you're not going to memorize them, but you should write them down because we'll be referring to them. Let's take a look at this example. A block and pulley system is initially at rest. When the 1.20 kilogram pulleys break, it's released. The 15.0 kilogram block accelerates until it hits the floor 30 centimeters below. If the pulley's radius is 10 centimeters, how much time will the block take to hit the floor? So here's what the sketch looks like. I'm going to walk you through this first example, and then you'll have a chance to do one on your own. But look at the diagram. Don't freak out. Remember, just in physics, you take one thing at a time. Don't try to do everything at once. We've got frame 1 and frame 2. Frame 1 is when everything's at rest on the left. Frame 2 here in the middle is when things are in motion. I have my mass of the pulley labeled m sub p. I have the mass of the block, m sub b, and we have the values there from the givens, 1.20 and 15.0. We have the distance it falls, s equals 0.30 meters, and we have the tangential acceleration of 0 when it's at rest. Now, we can clearly see here that we're talking about tangential acceleration because the rope itself makes a tangent line with the pulley, so it's easy to visualize. But the subscript t here is to distinguish tangential acceleration from angular acceleration, which refers to the spin rate, the increasing spin rate here. On the right, I have the radius labeled 0.10 meters. Got the same mass of the pulley and same mass of the block. Now, let's take a look at what's happening here. Well, we know that as the block accelerates downward, the pulley is going to accelerate as well. Its spin rate will increase. So we have an angular acceleration alpha. Okay, we've got a tension, and there's going to be a tension in this rope. Okay, as always, tension goes it's throughout, right? So tension goes down if we're considering the tension from this point, the point tangent to the pulley, and the tension is going up if we're considering the tension from this point, the hook on that block. Okay, and then as we've learned in an earlier section, tangential acceleration equals r alpha. We know that this proportion is true. We've derived it before. Tangential acceleration equals r alpha. And so that's this green vector here, the tangential acceleration. Now notice we also have Fw equals mvg. We always know that weight is mg. So the mass of the block times g will give us the weight. All right. Now the question is, how much time will the block take to hit the floor? So you can kind of see what we need to do. What we need to do is we need to find the tangential acceleration, the green vector. Because once we do that, we will be able to calculate how long it takes to fall. Okay, because that's going to be our acceleration, which will be different from g, obviously. But if we know how to calculate the time it takes for something to free fall, then we can do a similar thing using a different acceleration. So we definitely need to find AT. And once we find AT, we're going to be able to answer the question. All right, so let's set this up. Now first we know that torque equals force times distance, and so since tension is a force, I've got T, and since R is a distance, I've got R, and so torque equals force times distance, or torque times radius, and that's going to equal I alpha. Remember that that's the equivalent, or the rotational equivalent, of F equals ma, Newton's second law. All right, so we have torque equals TR equals I alpha. Now we're going to fill things in. TR equals 1/2 MPR squared alpha. Again, don't freak out. Don't freak out, because the 1/2 MPR squared is simply the moment of inertia for a disk. I'm going to quickly go back to that slide, right? These are moments of inertia. These are the ones that we'll be using in this class. And we can see that for a disk over here, top right, the moment of inertia is 1/2 mr squared. Okay, so we have 1/2 mr squared alpha. And now we're going to set up another equation, a force equation. Net force equals ma, that's just Newton's second law. And here the net force would be Fw minus T. We know that T is kind of slowing down the force, but we also know that since this block is falling to the ground, the Fw must be greater than the T. And so Fw minus T will be our net force, and that's going to equal mBAT. All right, and finally, since Fw is mBg, we have mBg minus T equals mB r alpha. Notice we replaced two things here. We replaced Fw with an equivalent expression, mBg, and we replaced A sub t with an equivalent expression, R alpha. Okay, now we are simply carrying those two equations forward. That's all we have here to start out this screen. And so filling in then, we have t times the radius, 0.10, equals 1/2 times mp, which is 1.20, times 0.10 squared alpha. And that ends up being 0.1t equals 0.006 alpha. And simplifying, t equals 0.06 alpha. All right, now turning to our next equation, we are filling things in. 15.0 is the mass of the block. So we put that in for MB, 9.81 we know, minus T equals 15.0 mass of the block times the radius times alpha. Okay, now evaluating 147.15 minus T equals 1.5 alpha. Negative T equals 1.5 alpha minus 147.15. T equals negative 1.5 alpha plus 147.15. And since I already found that T equals 0.06 alpha above, I now use that fact, and then we can set negative 1.5 alpha plus 147.15 equal to 0.06 alpha. Clearly we see that we can now solve for alpha, and so going through the algebra there, we find that alpha equals 94.327 radians per second squared. Now, that was a lot of work, but we're not done yet because we haven't answered the question. We want to find the tangential acceleration. Finding alpha, or angular acceleration, was merely a stepping stone. So we recall that tangential acceleration equals r alpha. Then we fill things in. And so we have the 0.1 there for r. Obviously 0.10, same thing, because we're going to end up rounding in the end, so it doesn't matter. We put in our alpha, 94.327. Okay. And then we have 9.4327 meters per second squared. That's the tangential acceleration. Finally, we're in a position to answer the question. So we remember our good old chapter 3 equations. Remember, these are our friends. We keep seeing them over and over again. The heart and soul of classical mechanics. Those 5 equations you learned in chapter 3. So the convenient one here is s equals VITT plus 1/2 ATT squared. Don't worry about the subscripts. I always put subscripts in just to clarify. I put VI here because that's the initial tangential velocity. So IT, initial tangential, is all that means. And AT, of course, tangential acceleration. All right, so now we can do some plugging and chugging. We know we have 0.30, that's a given. 0 because it starts at rest, VITT is 0. And then we fill in the AT that we just found, and we're going to solve for t. T squared equals 0.0636, and t equals 0.25 seconds. So in a quarter of a second, this block will fall. Now notice what we've done here. I'm going to quickly go back to the original sketch, right? I'm just going to go back to the original sketch. And let's look at what we've done here. All right, if there were no pulley mass to worry about, we could have done this problem just like free fall. Okay, we could have done this problem just like a freely falling block, because before, when we're doing pulleys, we never worried about the mass of the pulley. It wasn't a factor. But obviously in real life it is a factor. The pulley has mass, and therefore it has a moment of inertia. And so what we've done here is we've done a free fall problem that takes into account rotational inertia. And going once more through all that stuff, we end up with our final answer of 0.25 seconds. All right, now this one you're going to do partially on your own. I will get you started because a lot of this is new, and this problem actually introduces something that you wouldn't think of on your own. So I'm going to walk you through the first part, and then you'll do the rest. In the block and pulley system below, M2 is 120 kilograms and M1 is 95 kilograms. The pulley's mass is 0.85 kilograms and its radius is 3.0 centimeters. Neglecting friction, what will be the acceleration of M2? All right, so let's look at this sketch. This is a problem similar to something you did in Chapter 4. But of course, in Chapter 4, you didn't worry about moments of inertia or rotational motion. And so this is going to be a version of that problem. Okay, let's try to understand the sketch first. All right, M1 equals 95 kilograms, we know that. A sub t, this acceleration, even though it's horizontal, is going to match this acceleration, which is vertical, and we can see that that acceleration, since it lines up with the string that's tangent to the pulley, is tangential acceleration. All right, let's look at these tensions. Now, you might be wondering, well, why not just label it T everywhere? Isn't the tension the same throughout? Well, tension was the same throughout when you don't need to worry, or when you didn't need to worry about rotational inertia. But now that we're taking that into account, well, the tension is not equal. Now, it is true that T2 is close in value to T1, but they're not exactly the same, all right? And we're going to see why in a little bit. We have our radius, 0.03 meters. We have the mass of our pulley, 0.85 kilograms. And we have M2, 120 kilograms. So this is the sketch. This is the sketch that expresses everything in our givens. Now what I'm going to help you with is the equation setup, because that's not intuitive. All right, there will be a problem in the problem set very similar to this one. All right, so pay attention to the equation setup, and then be ready to do the rest on your own when I ask you to pause. All right, so this is our first equation. T1 equals m1 AT equals 95 AT. This is just Newton's second law. That's all it is. F equals ma. T1 is a force, so T1 is the F here, equals ma, m1 AT. And so we fill in, and we have 95 AT. So we have one equation. T1 equals 95 AT. Now for our next equation, FW2 minus T2 equals 120 AT. Again, we know that the blue FW2 vector is going to be greater in value than the red T2 vector, because if it weren't, it wouldn't fall. Okay, but the T2 vector is going to slow it down, and so the net force FW2 minus T2 equals 120 AT. Now, we're going to set up a torque equation. So the net torque equals T2R minus T1R equals I alpha. Now, here's the part that is not intuitive. Okay, and the reason it's not intuitive is because you're used to thinking of tension the same throughout. All right, but let's take a look at this and see why it has to be true. All right, net torque. Well, let's look at this torque here. T2 is causing a torque, as you can see. T2 is causing a torque because it's a tangential force. And a tangential force multiplied by a distance, or a radius, is torque by definition. So T2 is causing a torque, and that's going to be a clockwise torque. T2 is causing a clockwise torque. It's being opposed by T1, which is causing a counterclockwise torque. Yes, I know that the overall motion of the pulley is clockwise, but there's still a torque that we have to account for, caused by T1, which is also a tangential force. And T1 is going in the direction opposite to T2. All right, so we know that T2 is greater than T1, and here's how we know it. Okay, we know it because if it weren't true, if T1 were greater than T2, then the pulley would be going the other way, and that's impossible. If T1 were equal to T2, well, then the pulley wouldn't go anywhere. Now you might ask, well, but T was equal to T when we didn't take into account rotational inertia. And that's true, okay? But since we are now taking into account rotational inertia, right, and we do have torques to account for, we can see that the only logical way to set up the equation is to consider the T2R torque as greater than the T1R torque, because if it weren't, the motion would go the other way. Now, there's another way to kind of think about it too, qualitatively, is that, this M2 is going down, and as it's going down, it's being slowed not only by the tension, but also by the rotational inertia of the pulley. And because of that, there's more to put on the brakes for the T2 portion of the string than there is for the T1 portion of the string, which is going along with the fall. And so that kind of helps you to make some intuitive sense of why T2 also needs to be greater than T1. All right, so this is our torque equation setup. T2R minus T1R equals I alpha. And now I'm going to write the next part in green because these three green equations are going to be the basis for the main three equations of the system that we're about to solve. All right, rearranging terms, we have R times T2 minus T1 equals I alpha. All I did is factor out an R there. Okay, now we're going to fill in what we know from the givens. We know that FW2 equals 9.81 times 120. 9.81 is G, 120 is the mass. And we have 1,177.2 newtons. We also know that I equals 1/2 mr squared. That's the moment of inertia of a disk, and a pulley is a disk. And so we have 1/2 times 0.85 times 0.03 squared. And we end up with 0.003825 kilograms meters squared. That's our moment of inertia for this pulley. We're now going to carry forward the three green equations because those are the three equations of our system that we're going to be using. And so we've got them written as follows. T1 equals 95 AT, 1177.2 minus T2 equals 120 AT, and R times T2 minus T1 equals 0.003825 alpha. All right, now notice that we have three equations and four unknowns. So we have to reduce the number of unknowns. And so we're going to remember that a sub t equals r alpha. And now we can replace the a sub t's with r alpha. And so rewriting, we have t1 equals 95 r alpha, 1177.2 minus t2 equals 120 r alpha, and r times t2 minus t1 equals 0.000385 alpha. All right, now we have a system that you can solve. And I'm talking about this system here, all right, that I'm circling. This system here is completely solvable. All right, you can put in the value of r. That's one thing you can do to start out with. And then you're just going to have t1, t2, and alpha as your unknowns. And then you'll be able to see how to go from there. Okay, so you're going to pause the video now, and you will resume once you find a value for alpha. Okay, continuing then with the solution. 95 times 0.03 is 2.85, and so we have 2.85 alpha. 1177.2 minus t2 equals 3.6 alpha, since 120 times 0.03 is 3.6. And filling in the 0.03 for the r, we have the third equation. All right, so now, since we have three equations for three unknowns, the most convenient way to solve here is by substitution, because t1 equals 2.85 alpha. So I plug this t1 in here for this t1 that I'm circling now with the mouse arrow. And then t2 you can rearrange so that t2 equals 1177.2 minus 3.6. And that's why I put that expression in for t2 down here. And so I have 1177.2 minus 3.6 alpha. And then I just put all of that in, and I have a final equation in terms of alpha and constants. And so we can solve for alpha. Doing the algebra, we rearrange terms, we combine like terms, we're going to now distribute, and we'll end up with this expression, and then we can move alpha to the other side. And finally, the last step is to find that alpha equals 182.15156 radians per second squared. Now, the question is the acceleration of the block, right? And so the acceleration of the block is a tangential acceleration, and alpha is just an intermediate step. So now we're going to go back up here to the top right of the screen, and we're going to fill in what we can for a sub t equals r alpha. So we put in our r, we put in our alpha that we just found, and we find that a sub t equals 5.5 meters per second squared. And this is the final answer.
In the last chapter, when we were doing rotational kinematics, we saw that for each equation in linear kinematics, there is an equivalent equation in rotational kinematics. And so every linear equation, this is probably the pattern you've noticed so far, has a rotational equivalent. Now, we already saw in this lesson that tau equals I alpha is the rotational equivalent of F equals ma. So it's just Newton's second law. But we also have rotational work and power. So W equals tau theta is rotational work, analogous to W equals Fs. That would be the linear equivalent. And P equals tau omega is rotational power, just like P equals Fe or P equals W over T that we saw in an earlier lesson. Now, just as a reminder of why Fv is the same as W over T, it's just force times displacement over time. Now, if we think of that as force times displacement, all of that divided by time, that would be the average power, which is work over time. But if we think of it as force times displacement over time, then that's where Fv comes from. And similarly, that's what we have in tau omega. Now, we could write rotational power as simply tau theta divided by t. It'd be the same. That's the same as work over time. Now, the interesting thing about rotational work and power is that the units check out. And this is what you'd expect because work should always be joules and power should always be watts. Now, that might not be readily apparent when you look at tau theta, but let's remember that the units of tau, as discussed earlier in this lesson, are Newton meters. And of course, that's Newton meters as a vector, not a scalar. But still, it's Newton meters. And if you look at tau theta, you've got Newton meters times radians. But let's keep in mind, radians are non-units. What I mean by that is a radian is just a ratio, and it's just what you get when you do arc length divided by radius, right? Because if theta equals arc length divided by radius, that's the same as saying that arc length, or S, equals radius times theta. But the point is that if theta equals arc length over radius, arc length has certain length units and radius has certain length units. Those units will cancel, which means that even though we can write radians as rad, R-A-D, a radian is actually a non-existent unit. It's just a ratio. It's unitless. And therefore, tau theta is just Newton meters, which is joules. And similarly, if we look at tau omega, well, omega is just radians over time. And so what we'd have with tau omega is newtons times meters times radians divided by time. But radians is a non-unit. So then we just have Newton meters divided by time, and that, of course, is the definition of watts. All right, so rotational work and linear work, the units are joules. And with rotational power and linear power, the units are watts. And as usual, every linear reality has a rotational equivalent. And that's what we see here with rotational work and power. Incidentally, when you see the power rating of an electric motor, or the power rating of a gas engine, or if you are ever riding an exercise bike and they show you what watts you're producing, this is precisely the equation they're using. P equals tau omega. This is the power then of any rotational body, or body that is rotating.
All right, let's talk about rotational kinetic energy. So just as we have linear kinetic energy, which we talked about in Chapter 6, we also have rotational kinetic energy. So let's look at where that comes from. All right, for this rotating point mass, if we're just looking at the kinetic energy based on the definition we already learned, we can look at this thing's tangential velocity, Vt. And the definition of kinetic energy is 1/2 mv squared. And so the kinetic energy of this tiny particle, this point mass, is 1/2 mvt squared. Well, that equals 1/2 m r omega squared, since Vt equals r omega, as we learned in the last section. And then just simplifying, that's the same as 1/2 m r squared omega squared. All right, if you look at this guy here, that I'm kind of circling now with the mouse arrow, that's just r squared omega squared. Okay, and so you have 1/2 m r squared omega squared, and it doesn't matter where you put the parentheses. You can put them anywhere, so I'm putting them here since it's just a bunch of multiplication in a row. And so I'm left with Ke equals 1/2 I omega squared. Remember that the moment of inertia for a point mass, as talked about in an earlier slide here in this part 3, is mr squared. And so we simply replace mr squared with I. Okay, and so mr squared is replaced with I, and I'm left with 1/2 I omega squared. Now, you don't have to remember that derivation, but that's where the definition of rotational kinetic energy comes from. And so rotational kinetic energy for any rotating body is defined as KER equals 1/2 I omega squared. That's the definition of rotational kinetic energy for any rotating body. And as usual, since the formula for rotational kinetic energy is valid for a point mass, it's also valid for an entire body consisting of many point masses, because that body is just the sum of all the point masses. All right, the SI unit of rotational kinetic energy is just like the SI unit for any energy, okay? It's always joules. SI unit for any energy is joules. Total kinetic energy. The total kinetic energy of a rolling object is the sum of its linear and rotational kinetic energies. So KE total equals KEL, or linear kinetic energy, plus KER, or rotational kinetic energy. Now in Chapter 6, we were really only focusing on KEL, but now that we're talking about rotation, we can widen our horizons and take rotational kinetic energy into account. So KE total then, replacing it with our definitions, is simply 1/2 mVL squared plus 1/2 I omega squared. And don't be intimidated by this L here, it just means linear. So linear velocity, and linear velocity is normally a synonym for tangential velocity because tangential velocity goes in a straight line. Let's look at a few conceptual examples. A truck at the mechanic's garage, suspended off the ground, but with its wheels spinning, has only rotational kinetic energy. It's not going anywhere. It's just suspended. It's sitting in the mechanic's garage. He's working on it. He's got it suspended. He's got to look on the underside of the truck. All right, but he's got the wheels spinning. He's rotating the wheels. He might be running the car, checking how it drives, how the wheels rotate. All right, that truck has only rotational kinetic energy. It has no linear kinetic energy. It's not going anywhere. A truck rolling on a flat road has both KEL and KER. It's got both. It's moving along in a straight line, so that's where the KEL comes from. And his wheels are spinning, so that's where the KER comes from. A sled gliding on ice has only KEL. A sled doesn't have rotation. Right? A sled just slides, it glides. And so there is no rotational kinetic energy on a sled, only linear. Therefore, KE total is a combination of the two. And KE total is linear kinetic energy plus rotational kinetic energy. All right, continuing with this idea of total kinetic energy. If the two objects below, of the same mass and radius, are released simultaneously, the disk will reach bottom first. More of its gravitational potential energy becomes linear kinetic energy and less rotational. All right, this is kind of a neat thing. It's a consequence of the moment of inertia. Okay, we already talked a little bit about moments of inertia. And so you can either look at the table or recall some of the earlier sketches, but the ring is, the ring or hoop, whatever you want to call it, is actually going to have a greater moment of inertia because more of the mass is concentrated far from the axis of rotation, whereas with a disk, more of the mass is found close to the axis of rotation, so it's easier to roll. And that's why another way to understand this race, if you will, between the disk and the ring is that more of the disk's mass is close to the axis of rotation, and so it rolls faster than the ring. Therefore, if you're going to race these two, the disk is going to win. The disk is going to win the race.
Here I've got two disks which have the same radii. One of them is an aluminum ring, and the other is a piece of wood. Now, if these have the same mass, they have the same inertia, but they don't have the same rotational inertia because that mass is distributed in a different way. For this, the mass is distributed uniformly throughout. For the ring, the mass is all distributed far from where the axis of rotation will be, which is going to be right through the center. And so this will have a greater rotational inertia than this wooden disk. What we're going to have them do is race down this incline. And the one with the greater rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is 0. They're not rotating. Once I remove the piece of wood, one of them is going to rotate more quickly. Let's see which one that is.
Conservation of mechanical energy. So as you remember from chapter 6, when we talked about the conservation of mechanical energy, we had this equation as just the PE plus KE equals PE plus KE. Well, now that we're taking into account the rotational kinetic energy, we have to modify that equation a little bit. So PEGF, that is the gravitational potential energy at the end, or the final, plus KELF, linear kinetic energy, final, plus KERF, rotational kinetic energy, final, equals PEGI plus KELI plus KERI. Alright, so let's just look at this example. It's not a problem, but it's just a diagram to illustrate it. If we have this object, it could be a ball or a disc, whatever it is, it's just rolling down a ramp. It's rolling from height h, and it's rolling to the bottom of the ramp. And so the way this works is it's similar to what we learned in chapter 6. At first, all of the energy is potential, none of it's kinetic. And then at the end, at the very bottom, none of it's potential, all of it's kinetic. But that kinetic energy gets distributed differently depending on the moment of inertia. Some moments of inertia convert more of that potential energy into KEL. Some moments of inertia convert more of that potential energy into KER. But in any case, the total energy of the system remains the same, so that's why we call it conservation of mechanical energy. So in this system here, we see that the level of energy is 100 joules, and that remains the same throughout. It starts out as 100 joules of pure potential energy. Then about halfway down the ramp, it's got about 50 joules of potential energy, and then the kinetic energy, the remaining 50 joules, is spread between KEL and KER. And finally, at the bottom, we have no more potential energy, but all 100 joules are KEL and KER. Let's look at this example. A 10 kilogram ring of radius 12 centimeters rolls from rest down a ramp that is 60 centimeters high. At the bottom of the ramp, what is the ring's linear velocity? Remember that the VT, or tangential velocity of the outer edge of the ring, equals the VL of the whole ring, because that's just how wheels work. Here's the sketch. We've got a disc and a ring that are going to have a race. Okay, but for this problem, we're going to be focusing on the ring. We have the height labeled in meters, 0.60 meters. And we're going to start with our conservation of mechanical energy. And here we are also considering the rotational kinetic energy. All right, so this is our initial setup. PEGF plus KELF plus KERF equals PEGI plus KELI plus KERI. Now, the best thing to do in a problem like this is rearrange and do the algebra with the variables first. It saves you writing time. It saves you writing a lot of decimal places and all that stuff. Okay, and then at the end, when you have a fully simplified expression, then you do your plugging and chugging. So I'm going to walk you through this example, and then I'm going to have you do the next one on your own. All right, so PEGF, it ends at the bottom, and so it has a final potential energy, or gravitational potential energy of 0. 1/2 mVLF squared. That's because at the bottom it does have a certain final linear velocity, plus 1/2 I omega F squared, because it also has a final rotational kinetic energy. All right, mghi over here because it has an initial height, and so an initial gravitational potential energy, and 0 and 0 for KELI and KERI since it's starting at rest. Okay, now we just have a whole bunch of manipulation and algebra. To start off, let's remember that VLF equals R omega F, because we know that V equals R omega. Remember that if you look at this, sketch over here, we have a green VT vector going this way. We have another green VT vector going the other way because it's rolling. And the rolling causes an overall velocity of VL. And the VL is equal in magnitude to the VT because the VT is in contact with the ramp. All right, so VLF equals R omega F. That's nothing new. We learned that in part 1 of this chapter. And rearranging VLF over R equals omega F. Now this is going to be helpful to replace omega F in the next step, and that's what we are doing here. 1/2 m VLF squared plus 1/2 mr squared VLF over R squared equals mghi. Now again, before you freak out, why the mr squared? Why 1/2 I omega F squared becomes 1/2 mr squared VLF over R squared? Because mr squared is your I. mr squared is your moment of inertia for a ring. Now if you go back to the diagram that you should have faithfully copied earlier in this video, you'll see that the moment of inertia for a hoop or ring is mr squared. And we replace omega F with VLF over R, and so we have this expression. Now continuing on with our algebra, that simplifies to 1/2 VLF squared plus 1/2 R squared VLF over R squared equals GHI because we canceled the masses. And now we can multiply both sides by 2. Now we're going to carry this forward to the next screen. You can clearly see that a convenient step now is to cancel the R squareds. And so you'll end up with 2 VLF squared equals 2 GHI, which means VLF squared equals GHI, VLF equals root GHI, and now is the time to plug and chug. And we end up with 2.4 meters per second. So the final velocity of the ring is 2.4 meters per second. Let's talk about angular momentum now. So the definition of angular momentum, L equals RP equals I omega. Now this RP is kind of, you could say that it's somewhat intuitive. I'll just circle that RP because that's similar to some other things we've learned. You know, S equals R theta, VT equals R omega, AT equals R alpha. And once again, we have L, or angular momentum, equals R times the linear momentum. So you can see this pattern, the rotational equivalence of linear quantities. Basically, the bridge between them is R, the radius. It's just multiplying the radius by the linear quantity gives you the angular quantity. And so the linear momentum P times the radius will give you the angular momentum. And that equals I omega. Now we're going to prove the I omega part on the next screen, but this is just important to write the definition down. L equals RP equals I omega. The SI unit is kilograms meters squared per second. Kilograms meters squared per second. And that makes sense too, because if kilograms meters per second is linear momentum, well, you're multiplying that by R, and so you're going to have meters squared instead of just meters. Alright, so let's prove the L equals I omega thing, right? For this rotating point mass, L equals RP, that's by definition. And now plugging in MVT for P, because that's the definition of P, we can keep simplifying until we end up with mr squared omega. And since mr squared is simply the moment of inertia of a point mass, we replace mr squared with I, and we end up with I omega. And you can see how much I omega resembles mv. I is equivalent to, the mass or rotationally affected mass, and omega is equivalent, the rotational equivalent of linear velocity. So since this applies to the moment of inertia of a point mass, it also applies to the moment of inertia of any rotating body, because any rotating body is made up of many point masses. Alright, let's take this example. So taking the Earth to be a uniform sphere of radius 6.37 times 10 to the 6 meters and 5.98 times 10 to the 24th kilograms, calculate its angular momentum about its spin axis. Alright, so we're just going to calculate angular momentum. Now, you might be asking yourself, well, how do we know the omega? And I think some of you, probably most of you, can figure that out if you keep in mind how long it takes for the Earth to complete one rotation. Pause the video, try to calculate omega, and then resume when you have omega. Okay, so here's your omega. All right, if you figure this out on your own, great, good job. If not, no problem. But it's 2 pi radians because that's one complete revolution. One complete revolution in 24 hours. And so we have the conversions then. There's 1 hour for 3,600 seconds, and we end up with 7.27 times 10 to the negative fifth radians per second. All right, at this time, if you feel bold, you can pause and try to answer the question, angular momentum. If you don't feel confident, then just watch me walk you through the steps for the rest of this example. All right, so L equals I omega. That's the definition of angular momentum. And now we just plug in things. Remember those handy 4 moments of inertia of regular objects that I asked you to write down? Well, you should have referred to the solid sphere, all right? Because we know that the Earth is not a hollow sphere. And the moment of inertia of a solid sphere is 2/5 mr squared. So we're replacing I with 2/5 mr squared. And now it's just a matter of chugging and plugging, plugging and chugging. All right, so let's carry forward what we have. L equals 2/5 mr squared omega. And now we can plug and chug. And so we have our mass, we have our radius, and we have our omega. And we end up with L equals 7.06 times 10 to the 33rd kilograms meters squared per second. That is the planet Earth's angular momentum. Conservation of angular momentum. This is actually really neat. All right, so if the net external torque on a system is 0, the angular momentum is conserved. This is analogous to what we learned about the conservation of linear momentum, where if the net external force on a system is 0, the linear momentum is conserved. All right, so that's chapter 7 stuff. The most interesting consequences occur in systems that are able to change shape. So let's look at this. This is a system that's able to change shape. It's just a guy who's sitting on a swivel chair. All right, he's holding some dumbbells. And so his initial moment of inertia is, as you can imagine, or as you can see here, bigger than his final moment of inertia. Why? Because his radius goes down. All right. Initially, he has a big radius, then he has a small radius because he's bringing his arms in. And what's neat about this thing is because for angular momentum to remain constant, if he decreases the radius and therefore decreases the moment of inertia, then to make up for it, the angular velocity increases. So the angular momentum does not change. So what that means is this guy, if he's spinning slowly with his arms extended, once he brings his arms in, he's going to spin more quickly. All right. Now you've seen that happen with figure skaters, and I'll show you a little demo of that in just a little bit. But this is the physics behind that. Here's a great example of this. Look how the figure skater is going to enter a spin, and when she starts to spin, her arms are wide out, and then she brings them in and her leg in, and it achieves a very fast spinning speed. This actually happened in 2007. All right, so we know that the final momentum equals the initial momentum. So just as PF equals PI for linear momentum, in the same way, LF equals LI. And therefore, IF omega F equals II omega I. All right, so this will be our final example of the video. A figure skater with arm extended has a moment of inertia of 3.5 kilograms meters squared and a spin rate of 1.0 revolutions per second. By pulling her arms in, she reduces her moment of inertia to 1.2 kilograms meters squared. What will her new spin rate be? Okay, so keeping in mind that her moment of inertia is decreasing, and therefore her spin rate has to go up, then you should be able to use the conservation of angular momentum to do this problem on your own. All right, so pause the video, try and do it on your own, and then resume when you have an answer or if you get stuck. Okay, so basic equation, IF omega F equals II omega I. We know that the final angular momentum equals the initial angular momentum. And now we can do quite a bit of plugging in. And so we put in our IF, which is 1.2. We put in our II, which is 3.5. And we also put in our omega I, which is 2 pi. Now, why is it 2 pi? Well, you know that it's 1 revolution per second, and each revolution has 2 pi radians, and therefore omega I is 2 pi radians per second. That's why the 2 pi is put in for omega I. So omega F equals 18.326 radians per second. Since we've been asked to tell what the new spin rate is, then we have to convert that radians per second into revolutions per second. And we have the new spin rate equals 18.326 divided by 2 pi, since there are 2 pi radians in every revolution. And that equals 2.9 revolutions per second. That's her spin rate, 2.9 revolutions per second. So notice how, just kind of looking back to this problem, she has this initial big moment of inertia that becomes a small moment of inertia, and she has an initial small spin rate that becomes a big spin rate, 2.9 RPS, and therefore everything balances out and angular momentum is conserved.
Here's the classwork. Please write these numbers down, which will be on a worksheet posted later. See you in class.